These are the examples from R.8, linear, compound, and absolute value inequalities. This is part 2, and we'll cover the absolute value inequalities. This is example 6. We're going to solve the absolute value inequality. 3 times the absolute value of 5 minus x plus 2 is less than or equal to 14. Okay. First thing we want to do is isolate that absolute value. So anything that is outside the absolute value that's either added or subtracted to it is going to have to move over to the other side. So the first thing we're going to do is we're going to subtract this 2 over here with the 14. Alright, that's going to leave me with the problem 3 times the absolute value of 5 minus x is less than or equal to 12. Okay. Now the absolute value is still not alone because anything that's outside the absolute value that's multiplied or divided also has to move over. So let's divide both sides by that 3. They're going to cancel, and we are left with the absolute value of 5 minus x is less than or equal to 4. Okay, now in order to solve this, we're going to separate it into its two individual inequalities. And because this is a less than problem, this is going to be a compound inequality connected by the word and. And my two inequalities are 5 minus x is less than or equal to 4, or 5 minus x is greater than or equal to negative 4. Now notice what I did here. The original problem had a less than in it, this one has a less than in it, and there's my positive 4, and then to get to my second inequality, I turned the sign around, it was less than, now it's greater than, and I made my positive 4 into a negative 4. Oh, and I told you it was going to be an and I just put an or in there. Sorry. This is an and. Which means that when we graph it, we're going to be looking for the overlap between the two inequalities here. Alright, let's solve them. Over here, I'm going to subtract 5 from both sides. That leaves me with negative x less than or equal to negative 1. And let's divide that negative out of there, but that means that this sign right here is going to have to change direction. So x is actually greater than or equal to positive 1. Now let's switch colors here and work on the other inequality. I'm going to subtract 5 over here to this side. That leaves me with negative x greater than or equal to negative 9. And then when I divide by the negative 1, we have x greater than or equal to, nope, it's going to be less than or equal to, because I divided by a negative number. So that means my sign is going to have to change direction. This is going to be less than or equal to positive 9. Alright, let's see what the picture looks like when we draw it. Okay, we can put positive 1 down here, and of course we know 0 is smaller than that, and 2 is bigger than that. And we can put positive 9 up here, and 10 is larger, and 8 of course is smaller. Alright, let's graph these. The positive 1 is going to have a closed circle on it because of that greater than or equal to, and we're going to shade everything to the right of positive 1, like so, including the arrow right here. Let's do the other one. The positive 9 will also have a closed circle on it because of the equal to. And less than or equal to means we're going to be shading everything to the left here. Alright, so our graph is going to do something like this. And we are looking for the overlap between the two graphs. In other words, where on the number line do I see two graphs? Starting back here, I've got blue graph, blue graph, blue graph, blue graph. I get to this point, now I have blue and red. Blue and red, 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 blue and red. And I get to this point, and suddenly it's all red, 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 red. So the overlap occurs between here and here. Our set builder notation is going to be the set of X such that, and because we're doing the overlap, it looks like everything that's going to be included is right in here in between 1 and 9. So we want X to be in between positive 1 and positive 9. And we're going to put our little less than or equal to's in here, like so. And then for interval notation, the number furthest to the left that's included on both graphs is 1. The number furthest to the right included on both graphs is 9. And they are both going to get a bracket because they are both have an equal to in the problem. Example 7. Solve the inequality negative 18 is greater than negative 3 times the absolute value of 2y minus 4. I think the first thing I would like to do to this problem is turn it around so that the variable is actually over here on the left-hand side. So I'm going to change this into negative 3 times the absolute value of 2y minus 4 is less than negative 18. Anything that's located outside the absolute values that's multiplied or divided by it is going to have to move over to the other side, which means we need to start off by dividing both sides by this negative 3. Now they'll cancel. That sign is going to have to change direction because we divided by a negative number. That leaves me with the absolute value of 2y minus 4 is greater than positive 6. This is a greater than problem, which means that when I draw the picture of it on the number line, this is an OR problem. Where is the number line shaded? Anything that's shaded on the number line is going to be part of my solution set. Okay, let's get our two equations here. We've got 2y minus 4 is greater than 6. My connecting word here is going to be OR, because it's a greater than problem. And then my other inequality, 2y minus 4 is going to be less than negative 6. Now notice what I did, just like I did on the AND problem a minute ago. My original problem had a greater than 6, there it is. The second problem turns the sign around, so now it's a less than, and changes the sign on here. So it was positive 6, now it's negative 6. And then what we're going to do is we'll solve each of these individual inequalities, draw the picture, and write our solution sets. Over here, the 2y minus 4 is greater than 6. Let's add 4 to both sides. That leaves me with 2y greater than positive 10. And when we divide the 2 away, we have y is greater than 10. Now the other one. 2y minus 4 is less than or equal to negative 6. We're going to add the 4 to the other side. That leaves us with 2y less than negative 2. And when we divide both sides by 2, y is less than negative 1. So there are my two inequalities. Y is greater than positive 10 or y is less than negative 1. Now, let's take a look at the picture. We've got our positive 10 out here. Of course, 11 is bigger than that. 9 is smaller than that. We've got negative 1 back here. 0 is larger. Negative 2 is smaller. Let's look at the two pictures. For y to be greater than positive 10, We're going to want an open circle around the 10 because it's just greater than, and everything to the right is going to be shaded. For our second inequality, y is less than -1, again, we're going to want an open circle around here because it's just less than, and everything's going to be shaded to the left. The solution to this problem is everywhere that the number line has been shaded. So I have solutions over here in the pink area. I also have solutions over here in the purple area. So when I write my set builder notation, I'm going to need two parts to my rule to show that I had two pieces of graph shaded up here. We have the set of y such that y is less than -1, or, that's my connector word between them, y is greater than +10. So the y is less than -1, that's my pink graph rule, and then the y is greater than +10, that's my purple graph rule. And when I go and do the interval notation, the number furthest to the left on the pink graph, remember I need two intervals here because I actually have two parts of the graph shaded. So on the pink graph, the number furthest to the left is going to be -infinity. And still on the pink graph, the number farthest to the right is -1. And infinity gets a parentheses, and 1 gets a parentheses also because it's an open circle. On the other side, the purple graph, the number furthest to the left is 10. The number furthest to the right is going to be +infinity. And then infinity is going to get a parentheses around it. So is the 10 because 10 had an open circle. And then remember, to show that there were two places where I had solutions, I need to put the little union symbol in there to show that my solutions are here or they're over here. All right, let's look at some special cases for example 8. In the first problem, we've got the absolute value of x minus 3 is less than -2. This less than means that this problem is going to turn into a compound inequality connected by the word and I know that because it's a less than. We're going to have x minus 3 is less than -2, and its partner inequality, which is going to change my sign in the other direction and change the sign on the -2, will be x minus 3 is greater than +2. Now we'll solve each of these inequalities individually. I'm going to add 3 to both sides here. They're going to cancel. This is going to leave me with x is less than +1. And when I look at the other one, I'm going to add this 3 to the other side. This is going to leave me with x is greater than +5. Okay, let's take a look at this out on the number line. We've got a +1 here, and a 0 on that side, and a 2 on that side, and we've got a 5 over here, and a 6 on that side, and a 4 on that side. Now let's see what the pictures look like. For x is less than 1, we're going to have an open circle around the 1, and we're going to shade everything on the graph that's to the left of +1. For x is greater than +5, we're going to have a circle over here at +5, and we're going to shade everything off to the right of +5, like so. Remember, for these problems that are connected by the word and, we want all of the solutions that are on the green graph and they're on the orange graph at the same time. And you can see that there are no numbers on the green graph that are also on the orange graph at the same time. And what this means for part A is that this problem has no solution. All right, let's look at part B. For part B, we have the absolute value of x minus 3 is greater than negative 2. These are the problems that are going to turn into a compound inequality connected by the word or, and I know that because it is a greater than sign. Now I want to set up my two inequalities. The first one will be x minus 3 is greater than negative 2. Or, now we go to get the second one. The second inequality is going to change the sign from a greater than to a less than, and it's going to change my negative 2 into a positive 2. We'll have x minus 3 is less than positive 2. To solve these, in the first one, I will add 3 to both sides. We have x is greater than positive 1. And on the other side, I will add 3. We will have x is less than positive 5. Let's take a look at the picture. Once again, we have a 1 down here and a 0. 2 is larger. We can put a 5 at this end, and a 6 and a 4. Let's take a look at the graphs. X is greater than 1 will have a circle around 1, and everything will be shaded to the right. X is less than 5 will have a circle around the 5 and will shade everything to the left of 5. The OR problems, remember, ask you where the number line has been shaded. Anything on the number line that's been shaded is part of the solution set. So in our case, we take a look at the number line. Over here, the green graph has been shaded, so this part right here is part of my solution because it's green. We get to here, we jump up, we can see orange graph, and we have orange and green graph between here and here. So this part is also in my solution set because it's on the orange and the green, but remember it only has to be on one or the other. And then down here, we notice that the orange part has been shaded from here on. So all of this is included in my solution set as well. In short, my entire number line has been included, or will be included in the solution set because the whole thing has been shaded. And what this means for us for problem B, since the whole number line is shaded, it's all real numbers. All right, let's take a look at problem C. We've got the absolute value of x plus 1 is less than or equal to 0. Once again, I notice that the x plus 1 is less than or equal to 0 is going to turn into a compound inequality separated by the word and. And I know it's and because of the less than sign, right? All right, let's set up our inequalities. The first one is going to be x plus 1 is less than or equal to 0. And for our second inequality, we're going to have x plus 1, turn the sign around, greater than or equal to, change the sign on 0. Well, negative 0 doesn't make any sense here, so let's get rid of that negative sign there. And this is what we're going to draw. X plus 1 is less than or equal to 0, and x plus 1 is greater than or equal to 0. All right, let's solve the one on the left first. We subtract 1 from both sides. We're left with x is less than or equal to negative 1. And now let's solve the one on the right. If we subtract the 1 on both sides, we'll have x is greater than or equal to negative 1. Let's take a look at the picture. On the number line, We can put -1 right here. -2 is smaller. 0 would be larger. All right, for our blue graph, x is less than or equal to -1. It's going to give me a closed circle right here at -1, and we want to shade everything to the left. For the orange graph, we're going to put a closed circle around the -1 and shade everything to the right. And once again, we notice that for and, we are looking for the overlap. Okay, what points are included on both graphs? Where on the number line do I see two graphs, one on top of the other? Well, I've got orange, 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 orange until this point, and then I see I jump down to the blue, so there they line up. And then from here on out, I've got blue, 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 blue. So it looks like the only place where they overlap each other is right here at -1. And what that means for us as far as the solution set is concerned is that -1 is the only thing that will satisfy this inequality right here. Now let's look at part D. We have the absolute value of x plus 1 is greater than 0. I know that this is going to become a compound inequality separated by the word or, and that's because of the greater than sign here. Let's take a look at our two cases. Our first one, x plus 1 is greater than 0, or the second case, x plus 1, change the sign, so now it's less than, and change the sign on 0. And again, -0 doesn't really make any sense here, so let's get that out of there. Let's graph these and see what we get. Nope, let's solve them first. I'm going to subtract 1 from both sides here. So x is going to be greater than -1. And then for my second inequality, I'm going to subtract 1 from both sides. And x is going to be less than -1. All right, let's take a look at this on the number line. We can put our -1 right here, a -2 back here, and a 0 over here. The purple graph will have a circle over -1, and then we'll shade everything to the right, like this. The green graph will have a circle over the -1, and we'll shade everything to the left. The OR problems, remember, ask me where on the number line has it been shaded. So anything that has color is part of my solution set. So everything from here to here is part of the solution set because it's purple. And everything from here to here is part of the solution set because it's green. So it looks like the only thing I'm going to leave out is right here, the -1, because I've got two open circles right there. So when I go to write my solution set, I'm going to have two places because what's included here is going to be everything except -1, and that's not included because it's not shaded purple and it's not shaded green, but everything else is shaded either purple or green. How we write this in interval notation, we just write an interval for the green graph and we write an interval for the purple graph. Now the green graph goes from -infinity all the way to -1. and this is a parentheses, and the one's not included, so it's a parentheses. And then the purple graph goes from -1 all the way out to positive infinity. And this is a parentheses, and this is a parentheses because it's an open circle. And then remember, because I had two pieces of graph, I have two solutions. I need to put the little union symbol in here to show that my solutions are here or they're over here. Example 9 you can see is an application problem of these inequalities. For a recent year, the monthly snowfall in inches for Chicago, Illinois for December, November, January, and February was 2.0, 8.4, 11.2, and 7.9 respectively. How much snow would be necessary in March for Chicago to exceed its monthly snowfall average of 7.28 inches for these 5 months? Okay, so things that we know. First of all, we're going to be taking an average. An average just means that we add up all of our data and we divide by however many of them there are, and that tells us what the average is. The other thing is we've got the word exceed here, and exceed means this is going to be a greater than problem. So I want the snowfall average to exceed or be greater than the normal snowfall average of 7.28. All right, so let's set this up. We've got 2.0 plus 8.4 plus 11.2 plus 7.9. This is supposed to be divided by 5 because it's for 5 months. And we want this to be greater than 7.28. Well, if I go back up here and look, 2.0, that goes with November, 8.4 goes with December, 11.2 goes with January, 7.9 goes with February. They didn't tell me how many snowfall inches there were in March. That's what we're looking for. So we actually have to put our variable in here, and I'm just going to call it M since we're looking for the month of March. Okay, if we add our like terms over here, this is going to give me 29.5 plus M, and this will be divided by 5, and it's greater than 7.28. We're trying to solve for this M here. That means I should probably do something with this 5. Let's multiply both sides by 5 and eliminate the fraction. 29.5 plus M divided by 5, and we know those are going to cancel, is greater than 5 times 7.28. This is going to leave me with 29.5 plus M is greater than 36.4. All right, to solve for M, let's subtract the 29.5. That tells me that M is greater than 6.9. So there needs to be more than 6.9 inches in March in order for the average snowfall to exceed 7.28 inches.